Good afternoon, everyone. I am Professor Hangwon Bin at NJ University. I am excited to present our latest research on improving brain tumor segmentation using a novel model, the 3D Cascaded Dynamic Attention Unit, or ICU-NET. This presentation will cover the motivations behind our research, the methodologies we employed, the results we achieved, and our future directions. To begin, it's essential to understand the broader context within which our research is situated. Brain tumors are classified into two main types, benign and malignant. Both types pose serious health risks as they press on other parts of the skull and damage surrounding brain tissue. Early identification is crucial for effective treatment and better patient outcomes. Currently, MRI is the gold standard for brain tumor detection, providing high-contrast images for diagnosis and treatment. Precise segmentation is essential for clinical diagnosis and management. However, automated segmentation presents significant challenges due to the diverse sizes, shapes, and locations of brain tumors. UNET has become the preferred model for medical image segmentation due to its computational intelligence and efficient architecture. However, manually segmenting MRI images is tedious and time-consuming. The challenge is further compounded by the irregular and unclear borders, as well as the varying sizes and shapes of brain tumors. Deep learning has significantly advanced brain tumor segmentation tasks, making automated segmentation more feasible. Fully convolutional networks replaced fully connected layers with convolutional layers, allowing for pixel-level image classification. UNET was developed to address the limitations of FCNs, using symmetric encoders and decoders with skip connections, for better feature retention. 3D-UNET was proposed to improve segmentation performance by capturing contextual information in 3D MRI images. Further enhancements include the introduction of autoencoders, attention mechanisms, and cascade architectures to better handle small-scale and irregular brain tumor regions. These advancements make cascade networks a significant area of study in brain tumor segmentation. Building on the strengths of previous models, we propose the ICU-NET, a novel 3D cascaded BTS network design. This model integrates EMA and dynamic convolution into the UNET framework. The ICU-NET enhances the network's ability to capture features over long distances with a lightweight EMA module, showing competitive performance compared to state-of-the-art techniques. The ICU-NET architecture is a two-stage network that cascades to 3D-UNET networks with 4 layers of upsampling and downsampling. Initially, it segments brain tumors roughly, then refines the segmentation using aggregated information. The EMA module captures long-distance feature dependencies, enhancing global information representation. Dynamic convolution adapts its kernel based on the input, improving feature capture for tumors of various shapes and sizes. In the second stage of ICUNet, all regular convolutions are replaced with dynamic convolutions. This enhances network performance without increasing its depth or width, making it more efficient. The ICUNet utilizes a two-stage loss function approach, combining cross-entropy and dice loss functions. This addresses class imbalance and improves segmentation accuracy. The training process involves computing these loss functions independently into stages, then combining them for final supervision, resulting in improved network performance. Our experimental setup included a 3.80 GHz Intel Xeon CPU and a 24 GB NVIDIA RTX 3090 GPU for model training. Python and the Atom Optimizer were used for implementation. We tested our model on the BROT-ES 2019 and BROT-ES 2020 datasets, using various MRI images for training and validation. To measure performance, we used the dice similarity coefficient and Hausdorff distance. The dice score measures the overlap between the predicted and ground truth segmentations, while the Hausdorff distance evaluates the boundary distance between the segmentation result and the ground truth. These metrics provide a comprehensive evaluation of our model's accuracy. We conducted ablation studies on the BROT-ES 2020 dataset to validate the efficiency of ICUNet. The results showed significant improvements in DSC values for ED, WD, and TC compared to baseline models. These findings demonstrate the effectiveness of the proposed modules in enhancing segmentation performance. ICUNet was compared with other representative methods on the BROT-ES 2019 and BROT-ES 2020 validation sets. Our model outperformed others in terms of DSC and Hausdorff distance, demonstrating its competitiveness in the field. Visual segmentation results further showed that ICUNet effectively segments enhancing tumors, WD, and tumor cores. In conclusion, the introduction of EMA and dynamic convolution modules significantly enhanced the network's ability to capture both global and local tumor information. Our experiments on the BROT-ES 2019 and BROT-ES 2020 datasets demonstrated the effectiveness of ICUNet. Future work will explore more sophisticated data augmentation techniques and post-processing methods to further improve segmentation accuracy. Thank you for your attention. I am happy to take any questions you may have.